Hi guys, my name is Brittany. Thank you so much for coming back to a new statistics video. If you're new here, I am a teaching assistant at the Georgia Institute of Technology for their industrial engineering department, and I help teach a probability and statistics course. If you'd like to check out more videos on probability and statistics fundamentals, you can click somewhere here or here, or I'll just leave it down in the link below. So let's get started. Today we're going to talk all about binomial random variables and their probability distribution. So let's note that this is a type of discrete random variable and a type of discrete probability distribution. So binomial random variables are defined by a random experiment in which it comprises Bernoulli trials. So to go on a quick side tangent, let's talk about what a Bernoulli trial even is. So a Bernoulli trial has two possible outcomes. It'll either be a success or a failure. And secondly, all these trials are independent of each other. And thirdly, we can say that the probability of a success occurring within one of these trials is constant for each trial. And we can represent the probability of a success occurring, saying a little lowercase letter p. Going back to talking about binomial random variables, we can say that our binomial random variable, let's just say a capitalized letter x, represents the number of success trials. So let's talk about the probability mass function, or for short, a PMF, for a binomial distribution. So as we know, we can represent a PMF as a little f of x function, which is equal to the probability that our binomial random variable is equal to some instance, and that's equal to the combination of n and x, which we'll talk about in just a moment what those two things stand for, multiplied by the probability of a success raised to the power of the number of success trials, or the letter x, multiplied by 1 minus this probability to the power of n minus x for all cases of our random variable x, starting from 0 and counting consecutively to some number n. So in this equation, we can say that p stands for the probability of a success, n will stand for the total number of trials that occur, and x will be the number of specifically success trials. Alright, so when talking about binomial random variables, we can also talk about their mean and variance, which are other statistics that we can use to describe their discrete probability distribution. And so a mean can be represented as the Greek letter mu, which is equal to our function e of x. And in this case, for a binomial random variable, we'll describe this as the total number of trials, or n, multiplied by the probability of success. And secondly, for variance, we can denote this as sigma squared, which is equal to a v of x function, which is equal to n times p times 1 minus this probability, which is also equal to our mean, multiplied by 1 minus the probability of success. So a lot of this might seem like a bunch of letters and numbers right now, so let's actually apply this in a real-world example. So let's say, for example, that the probability we score a goal in a soccer match has a 62% chance. So what's the chance that we make exactly 3 shots if in a match our team takes exactly 5 opportunities to shoot on the goalie? So firstly, before we start even doing any math, let's ask ourselves, can we use a binomial PMF to solve this problem? Well, firstly, let's see if Bernoulli trials are being conducted. So a Bernoulli trial consists of 2 possible outcomes, a success or failure. So in this case, we can define our success as a goal being scored on our goalkeeper, and a failure can be defined as missing our shot. And from this example, we can also assume that these trials are naturally independent. And secondly, let's also note a couple key fundamental characteristics of a binomial distribution. So in a binomial distribution, we have a known specified number of trials and an unknown number of successes that we want to find the probability for. So in this specific example, we know that we have exactly 5 trials. So we're shooting 5 times on the goalkeeper, and we want to find the probability that we make exactly 3 shots. So we want to find the chance of 3 successes. And in this case, these successes can occur in any order as long as they're within the 5 shots. And so for example, if we have, let's just say 1, 2, 3, 4, 5 shots, and we say that we make 3 here, here, and here. So our successes can occur anywhere as long as they're within the 5 trials. For example, in another case, we could also still have 5 shots on the goalkeeper, but make our successes our first, second, and our last one. And so everything that's not a success will be a failure, since it's a Bernoulli trial, and there are only 2 possible outcomes, success or failure. And so we can denote this as the complement of our probability, in this case putting a not symbol. And so these are just a couple examples of different combinations that we can have in which we have exactly 3 successes within 5 known trials, in other words, 5 shots on the goalkeeper. So in this case, we can call our random variable x a binomial random variable, and so we can use our binomial equation for a probability mass function to solve. So we know that our PMF is, again, a little f of x function in which this is equal to the probability of our random variable x being equal to some instance. And in this specific example, we want to find the probability of exactly 3 success goals. So our random variable x in this case will be equal to 3. And since we know the number of specified trials is 5, we can say that our variable n, which is the total number of trials, is equal to 5 shots on goal. And the probability of our success we know is 62% or 0.62. So p is equal to 0.62. And to solve this, we'll just use our equation from earlier, plug in our known variables. You can also note here that this is a combination. So of 5 shots, of 5 total trials, we choose 3, or we have 3 success goals. And that'll be the probability that if we take 5 shots on the goalie, we know that we take exactly 5 shots, that will make exactly 3. All right, and just to expand this even further, let's find our mean. So that's our mu being equal to e of x, which is equal to, as we saw earlier, n times p, so 5 times 0.62. And our variance would be sigma squared, which is equal to v of x, which is equal to, again, our equation from earlier, n times p multiplied by 1 minus the probability of success is equal to 5 times 0.62, which is, in this case, our mean, multiplied by 1 minus 0.62. And that'll be our solution for the variance of this binomial probability distribution. All right, and that's pretty much all for today. If you have any questions, just leave them down in the comments below and I'll be sure to get back to you. All right, thank you so much for tuning in and I'll see you next time. Bye.